Einstein's discovery that time could stretch and compress revealed that the space-time fabric itself was far more dynamic than humans had ever imagined. The rigid, mechanical universe that Newton described gave way to a cosmos where space and time formed a unified structure that could bend and warp. But Einstein's revolutionary insights about space-time would soon reveal an even more profound mystery about the fundamental forces that shape reality itself. Gravity's hidden secret. Newton described gravity as a mysterious force that reached across empty space to pull objects together. The sun somehow attracted Earth from 93 million miles away without any visible connection between them. Apples fell from trees because Earth exerted an invisible pull on them through the vacuum of space. This concept worked perfectly for calculating planetary orbits and predicting motion, but it left a fundamental question unanswered. How could massive objects influence each other across vast distances of nothingness? What mechanism allowed this force to operate through empty space without any physical medium to carry it? Einstein proposed a revolutionary alternative that eliminated the need for mysterious forces acting at a distance. Massive objects like the sun do not pull on surrounding matter through some invisible force. Instead, they curve the fabric of space-time itself, creating geometric distortions that guide the motion of nearby objects. Mass warps the structure of reality, bending the four-dimensional framework of space and time into curves, valleys, and hills that determine how everything moves through the universe. The standard model for visualizing this concept involves imagining space-time as a flexible rubber sheet stretched flat. This represents the undisturbed fabric of space-time in empty regions of the universe. When a massive object like the sun sits on this sheet, it creates a depression that warps the flat surface into a curved valley, extending outward from the object's position. The greater the object's mass, the deeper and steeper the depression becomes. This curved geometry represents how massive objects form space-time around them. Objects moving through this curved space-time naturally follow the contours created by these depressions. They appear to be pulled toward massive objects, but no force actually attracts them. The objects simply follow the straightest possible paths through the curved geometry of warped space-time. What we perceive as gravitational attraction is actually objects moving along the curved pathways that mass creates in the four-dimensional fabric of reality. Planets orbit stars not because of any pulling force, but because the curved space-time guides their motion into elliptical trajectories. Earth's enormous mass creates a steep valley in space-time with the deepest point located at the planet's center. This valley becomes progressively shallower as distance from Earth increases, creating weaker gravitational effects at higher altitudes. Objects near Earth's surface experience strong curvature effects because they sit deep within this space-time valley. Satellites in orbit occupy regions where the valley is less steep, experiencing weaker gravitational effects that allow them to maintain stable orbital trajectories around the planet. The curvature varies dramatically with distance from massive objects, following precise mathematical relationships that Einstein calculated. This variation explains why astronauts on the International Space Station experience microgravity despite being only 250 miles above Earth's surface. They orbit within a region of space-time where Earth's gravitational valley is shallow enough to allow continuous free fall around the planet. The same principle applies throughout the solar system, where planets orbit the sun by following curved paths through the space-time valley created by the sun's massive bulk. Gravitational wave detectors in 2025 can measure ripples in space-time with extraordinary precision. The Laser Interferometer, Gravitational Wave Observatory, and the Virgo detector monitor space-time. Distortion smaller than 1/10,000th the width of a proton. These instruments detect the passage of gravitational waves created when massive objects like black holes or neutron stars accelerate through space, creating ripples that propagate outward through space-time at light speed. The successful detection of these waves provides direct evidence that space-time behaves exactly as Einstein predicted. Recent observations of black holes have confirmed Einstein's predictions about extreme space-time curvature. The Event Horizon Telescope captured images of the supermassive black hole at the center of galaxy M87, revealing the shadow cast by the black hole's event horizon against the glowing matter spiraling around it. This shadow appears exactly as Einstein's equations predict for an object so massive that it creates nearly infinite curvature in space-time. The light from matter approaching the black hole follows the curved space-time paths, creating the distinctive patterns observed in these historic images. Black holes represent the most extreme example of space-time curvature possible in the universe. Their massive density creates such steep valleys in space-time that nothing, not even light, can escape once it falls past the event horizon. The curvature becomes so severe that it essentially creates a one-way path through space-time, allowing matter and energy to fall inward, preventing anything from traveling back outward. These extreme conditions provide natural laboratories for testing Einstein's most radical predictions about the behavior of curved space-time. This curved space-time concept leads directly to gravitational time dilation effects that influence every moment of our lives. Time passes at different rates depending on the depth of the gravitational valley an observer occupies. Clocks run slower in stronger gravitational fields because time itself follows the curvature of space-time. The deeper an observer sits within a massive object space-time valley, the more slowly time passes relative to observers in weaker gravitational fields at greater distances. Even on Earth's surface, precision instruments can detect time differences caused by elevation changes of just a few meters. Atomic clocks at sea level run measurably slower than identical clocks on mountaintops because sea level positions sit deeper within Earth's gravitational valley. The Atomic Clock Ensemble and Space Mission, launched in April 2025, tests these effects by comparing atomic clocks aboard the International Space Station with identical clocks on Earth's surface. These measurements reveal exactly how gravitational curvature affects the passage of time throughout different regions of Earth's space-time valley. Einstein's insight transformed gravity from a mysterious force into geometric properties of space-time itself. Mass and energy curve the fabric of reality, creating the paths that all matter and energy must follow. This geometric understanding revealed that the most extreme gravitational environments in the universe would produce the most dramatic demonstrations of time dilation effects where the passage of time could slow to almost unimaginable degrees. The Interstellar effect. The movie Interstellar presented audiences with one of the most dramatic demonstrations of time dilation ever depicted on screen. Astronauts descended to a planet orbiting dangerously close to a massive black hole, where the gravitational effects created extreme time distortion. Every hour spent on that planet's surface equaled 7 years passing on Earth. The crew members who remained on the spacecraft watched decades slip away while their colleagues experienced only a few hours on the planet below. This scenario represents a completely accurate portrayal of Einstein's gravitational time dilation predictions. The planet in Interstellar experiences such intense gravitational effects because it sits deep within the black hole spacetime valley. The massive black hole warps spacetime so severely around the planet that time itself slows to a crawl compared to regions with weaker gravitational fields. This extreme time dilation occurs because the planet occupies a position where spacetime curvature reaches enormous proportions. The gravitational field strength becomes so powerful that it dramatically affects the fundamental rate at which time passes for anything on the planet's surface. This dramatic time difference follows directly from Einstein's field equations, which describe how mass and energy curve spacetime. When applied to the extreme conditions near black holes, these equations predict exactly the kind of time dilation effects shown in the movie. The precision of Einstein's predictions allows scientists to calculate these effects with mathematical certainty. Black holes create the most extreme space-time curvature possible in the universe, leading to the most massive time dilation effects found anywhere in nature. Their enormous mass compressed into incredibly small volumes generates gravitational fields so intense that they warp space-time beyond anything found around normal stars or planets. Near a black hole's event horizon, time dilation becomes so extreme that an outside observer would see time essentially stop for anything falling toward the black hole. The Event Horizon Telescope's observations of real black holes have provided unprecedented measurements of time dilation effects in their vicinity. Scientists can now observe matter spiraling around black holes and measure how time passes differently at various distances from these massive objects. Gas and debris orbiting close to black holes show clear signatures of time dilation, with material closer to the black hole appearing to move and emit light at rates that differ dramatically from material farther away. These observations reveal space-time curvature gradients that create measurable time differences across relatively small distances near black holes. Matter on the inner edge of an accretion disk experiences significantly different time passage compared to matter on the outer edge. The time dilation effect creates observable differences in the frequency and timing of light emitted from different regions around the black hole, providing direct evidence of Einstein's predictions about extreme gravitational environments. Different planets throughout the universe with varying